And we're back once again. We're computing the predictive distribution for the Bayesian linear regression model. And we are hot on the trail. We're just about to nail this thing. So we got down to this step where we were, let's briefly recap here. We're trying to compute this predictive distribution, probability of y given x in the data. And our goal was we integrated out the y part. We got this function of x. And then our goal is to express this as a normal over y, proportional to a normal over y. And we just about got it here, you can see, because we've got this quadratic looking thing in y. And we'll do the same sort of trick that we did before. To complete the square, now we can be lazy. So what are we going to do? We want to get this to look like the exponent of a Gaussian, or at least, after you pull out the -1/2 to look like the exponent of a Gaussian, and then the exponent of a Gaussian in that case is some precision. I'll put lambda. Sometimes people use lambda for the precision, and this is just a scalar quantity, times y minus the mean, let's say mu, not mu, u sort of sounds like mu, squared. And this, if we multiply it out, well, of course, it's just lambda times y squared minus 2 lambda uy plus lambda u squared. And we want to match these up, so we should choose, what should we choose? We want to match this up with this, so we should choose lambda equal to a squared. Oh wait, no, we can't, we're not quite ready for that. First we have, that's m transpose lm. We want to match it up with this part, so we need to write what this is, a y squared minus m transpose lm equals, let's pull together and that's minus this, so this is going to be a minus a squared x transpose L inverse x y squared minus 2ax transpose L inverse lambda mu y plus constant. So now we want to match it up, and what do we do? Let's see. So we should take lambda equal to this part, a minus a squared x transpose, let's go ahead and pull out an a, may as well, a times 1 minus a x transpose L inverse x, and we should take u, let's see, we want to match this up with this, so we need lambda u equal to this part, so we may as well take u equal to 1 over lambda, that's supposed to be a lambda, times this, a x transpose L inverse lambda mu. And so we got this thing in this form. We can go ahead and should we write it? Let's go ahead and write it, I guess. So this is, right, let's go back here. Our posterior predictive is proportional to e to the -1/2 times this. Posterior predictive is proportional to e to the -1/2 times this, and that equals this. So this is, well, let's go ahead and just write it. This is what is this? This is lambda, we'll plug it in, I guess. Lambda y squared. No, we don't need to plug it in. So we can just be lazy. We can just go ahead and write down what we have. I think you know this enough by now. We can just skip that. This is proportional to e to the -1/2 times this, and that was equal to this plus something which is constant with respect to y. So therefore it's minus lambda over 2 times y minus u squared, right? If we plug these in here, then we get this, which is equal to this, plus something which is constant in y. This is constant in y, this is constant in y. And so it's proportional to this. And that gives us the result. That's it. Well, almost it. There's one more step. So I worked this out ahead of time. I'm not doing this all on the fly. I worked this out ahead of time. And there's a little bit more. We can clean these up a little bit. And let me go ahead and write down what we can clean these up to be. U, and this is a non-trivial calculation actually. At least I didn't see an easy way to get it. U, it turns out, this thing is equal to mu transpose x. So that's a little tricky to see, but we're going to check that. And lambda, it turns out, or let's say 1 over lambda is now the variance, is 1 over a plus x transpose lambda inverse x. So this thing, the posterior distribution, or the predicted distribution on y given x and d, is normal with these parameters. So it's, let's go ahead and write that, is normal over y with parameters with mean u and variance 1 over lambda. And that, we could stop right there because we have now the predictive distribution in closed form. Well, with these expressions at least, we could just compute these, and these are closed form expressions for lambda and u, and this gives us the predictive distribution. So we finally finished our plan. We got this in a Gaussian form. So that's it. That's the predictive distribution. And this has a nice sort of natural interpretation because mu, if you remember, mu was the posterior mean. Maybe we should go back up to remind ourselves. But way back up, mu was the posterior mean for w. That was this vector. That was the posterior mean. So this was like the well, it was actually the maximum a posteriori. We saw that in an earlier video. And so this is like if you were to just take the mean of this predictive distribution, that would be like taking the map estimate of w and using that as your w. So it would be like the w transpose x for the map estimate of w. And so this is a very natural, that's a very natural thing to have for your mean of your predictive distribution. And now, so I want to show you how to compute these. It's actually a little bit tricky. It took me a little, so this whole calculation, I mean this whole thing, it took me about 3 or 4 times. I kept making mistakes and it took me quite a while to get this all straight. And this last little part is a little bit tricky. So let's see how to do this. Okay. It involves a certain linear algebra identity. So our goal, so we have u is equal to this thing. First let's do, should we do u first? Let me see, hold on a sec. Oh, actually, we might be able to do it without using that linear algebra identity. Let's see. Okay, so I think we might be able to do that. Let's see. So what do we want to prove? Let's first do the one for lambda. I think that's going to be easier. So we would like to show this. And we have this. So let's play with this a little bit. I think this is going to be pretty easy. So lambda equals a times 1 minus a. Let's call this thing, let's call alpha X transpose L inverse X, because that's going to pop up a lot. I don't want to keep writing that. So lambda equals A times 1 minus A alpha. And so 1 over lambda equals, wait, is that right? Hold on. 1 over, oh no, sorry, that's not what I want to call L. I want to call, okay, so we do need that linear algebra expression. So let me undo this stuff. Let's back up here. Okay, so we're going to use the following linear algebra identity. L, where's L? L was this thing. L was AXX transpose plus lambda. And we want to invert L. So we're going to invert L using the following. Right? We need to invert L so we can compute this. Lambda. L, that was AXX transpose plus lambda. And so the inverse is the inverse of that. And there, it turns out there's a great little linear algebra identity called the Sherman-Morrison identity or theorem that allows us to invert this. It's called a rank 1 update formula. So this equals the inverse of lambda minus lambda inverse A x x transpose lambda inverse divided by 1 plus A x transpose lambda inverse x. That's by the Sherman-Morrison theorem. And now let's call, this is what I wanted to define as alpha. X transpose lambda inverse x. Let's define that to be alpha. So we can simplify this a bit. We just plug in our definition of alpha. Well, I guess we can't simplify it a lot. Let's use that later. All right, so now we want to compute lambda. And lambda is this A times 1 minus... Actually, first let's compute X transpose L inverse X. We'll be able to, I think we'll be able to simplify that using this. So by linearity, this becomes alpha, and this becomes, we can pull out the A, and we get alpha squared divided by, I'm just multiplying these X transpose and X through on both sides of L inverse here, divided by, and this just stays the same, A times 1 plus A times alpha. Plug that in once again. And now let's compute lambda. Finally, we get to compute lambda. A times 1 minus A alpha. No, not alpha. A times 1 minus A times this thing. Times alpha. I'll just write it. This is just from this point on, it's just basically calculations. Just straightforward calculations. A times 1 minus, I'll write it out so I don't make mistakes. A squared A alpha over 1 plus A alpha. That's right, I think. 1, 2, blah, blah, blah. Yep. That's right. And then we can do, let's multiply, get a common denominator. We get 1 plus A alpha minus A squared alpha plus A squared. Oh, alpha squared? What's going on? It's unfamiliar. Is this right? Okay, I'm out of time. We're going to have to come back and finish this in another video. Alright, see you soon.